right, thank you very much, Vandalay, and thank you very much for being here. So could we start my slide presentation? All right, thank you. So what I would like to tell you about is the excitement of experiments, being carried out in very many different systems on exploring the quantum world with completely new tools, especially what we call the world of quantum simulations and quantum computing a little bit, and that might be a good point for discussion later. So what we are interested in are so-called many-body quantum systems or quantum many-body systems. It's an arrangement of many particles that have emergent properties, and this could be things like interesting materials that might help to address some of the questions we raised this morning in the context of climate change, superconductors, for example, topological materials. And Christiane de Morais-Smith will tell you actually much more about these materials, but it actually also pertains to complex objects on an astrophysical scale, such as neutron stars. There are also many-body systems that act according to the laws of quantum mechanics, and we have a fundamental interest in understanding those and gaining a better understanding how they work. So what's the problem? So the problem is not that we don't know the laws by which they interact. The laws are the laws of quantum physics and electromagnetism, Maxwell's laws. And so what we really don't know in many cases is how to calculate emergent properties when many of those quantum particles come together, acting under these very well-defined laws to predict what the outcome of such interplay of many particles is going to be. And the reason for that is what we call quantum complexity, so let me explain that briefly to you. So imagine you have a hard drive and each information bit would be represented by a small magnet pointing up or down. We call these the spins, for example. So this would be all in 0 state, this would be all in state 1, or this would be some information stored on your hard drive. What's important that on a classical system, you only have one of those configurations present in the in the classical hard drive, the information that is stored on your hard drive. And what's so different about the quantum world, and this is what Anton told us about in superposition, and this is now becoming even more radically prominent for many particles, that you can be in different configurations simultaneously. And we call this the state of the quantum system, psi. And if you ask, how many configurations are there if I give you n particles, you actually find there's an exponentially increasing number of configurations. So already for a modest number of 300 spins or magnets that you want to store the state on your classical computer, we don't have the memory capacity. In fact, the memory would have to be as large as we anticipate today the entire number of protons in the universe. So even our supercomputers, this is one in Munich across the street of MPQ, cannot do many of those calculations. Of course, there are approximation methods, very powerful ones, but this is the problem, this exponential scaling of the configuration space in quantum physics that's really hard to tackle with quantum computers. So here comes the idea of Richard Feynman in '82, who in a very foresightful talk already foresaw, well, if we can't do that with classical systems, well, why don't we take a quantum system to simulate the dynamics or compute the behavior of another quantum system? And that was the birth of the idea of quantum simulation and quantum computing. And this is what people are so excited today about, because it really gives us new opportunities for fundamental understanding, creating new kind of sensors, new systems, useful technologies using such approaches. So today there are two approaches that people are pursuing. One is what we call the quantum analog quantum simulation approach. The idea is basically that you implement the physical system directly on your quantum hardware that you're implementing in the lab, and you study the behavior of the system. So you really should think of this as a synthetic material approach. You're really trying to synthesize a material in an artificial way that I will explain in a second. And this is a very powerful approach, but it's non-universal because you can only simulate what you can realize. Then there's, of course, the approach you've heard about also of quantum computing, which builds up this rule set by discretizing it into elementary operations, very similar to a classical digital computer, where now gates become quantum gates that you have. And this is nice because in principle it's universal, but it's very resource hungry. And I really want to caution, I'm very excited about this field of research, but to say that these approaches will, for example, accelerate AI by a factor of 1,000, we have no evidence for that. So I'm really excited, but I really want to caution making any false statements like that is not good for the community. And as much as I hope we'll see a lot of progress, we should be cautious of what we can really predict with these systems, what's going to happen. So by now, there are many actually systems people are pursuing to do this. So there are ions, atoms trapped in lattices, which I'll talk about now, atoms trapped in very tiny focused laser beams, so-called optical tweezers, superconducting devices. So I would say right now, quantum simulation has in fact become the major application field across all of those platforms that people are looking into. So we are studying this system of optical crystals, optical lattices. So this is actually a picture from Ted Hensch, who unfortunately can't be with us today. But you see actually the interference pattern. So several laser beams overlapped, giving rise to this beautiful pattern of light. So it's just a pattern of light, bright and dark spots. And the amazing thing is this immaterial crystal of light is able to trap material particles. So we can load very cold atoms into these crystals of light, and they are trapped in this light structure, and they move around in this light structure very similar to electrons in real materials. So the advantage is here now we can do this with several thousands of atoms. Everything is 10,000 times enlarged compared to real materials, so we can really look very nicely into these systems. I'll show you pictures of that in a second. And the motion is associated with this larger scales dramatically slowed down by a factor of 100 million compared to real electrons in real materials. So you can really also see how these particles roam about and interact with each other in these real materials. There's a price you have to pay. There's never a free lunch on these things. And the price we have to pay is that we have to work at really, really cold temperatures. We have to cool these systems using fantastic techniques that Bill was one of the inventors actually to bring them down to these temperatures. But if we do everything right, you know, we have now a fantastic opportunity because we can really now start to see, I call it more prosaic here, the dance of electrons inside a material, inside of this synthetic quantum material that we cannot look at in real materials. So how do we do that? Remember, we have this state psi, and we can have the system be in different configurations. Now, one thing Anton also told you is whenever you look at a quantum system, it's very different from a classical system because you actually destroy the original quantum system, and one of the configuration appears in your measurement device. For example, this one that you can see here, we call this the collapse of the wave function. And here's actually a beautiful picture of this collapsed wave function. This is real data, where you can see each blue spot is an individual atom held in this immaterial crystal of light, observed now with optical techniques through this quantum gas microscopes, and we can see it because remember, these are 10,000 times larger spacings than in real materials. So we can look at phase transitions in these systems. We can shape the potentials by just projecting light fields onto these atoms, and we can even move atoms around. I'll show you a movie in the end of how we do that. Just maybe this slide a bit more maybe for the experts. You remember, we can think of these atoms as like small magnets in our traps, and we can really also see how they're pointing, in which direction they're pointing, in which direction they're ordered. Here you can see on the left this, what we call antiferromagnetic pattern, where the magnets are pointing in an alternate fashion, and we get real space images with single lattice site resolution and single atom sensitivity, and that's a completely new way of looking at these materials, of understanding these materials. One application I was actually just to show you that it really has impact on material science. We actually, before this paper on a new superconductor, a material that can conduct electricity without resistance, we actually thought of a new mechanism for pairing mechanism to realize such high temperature superconductors. And then actually, we found that actually this material realized this. And so, by thinking through this approach and having these new ideas, I think we're really gaining also new ideas on how to construct materials to have useful properties in the end. So what are people now doing? What's the most exciting things people are working on right now? We're trying to combine this analog mode with the digital mode of quantum computing. This seems to be a most promising path forward right now in analog-digital hybrid operations. And just to give you a few ideas of research throughout the world, there's fantastic work coming out of China from Janwei Pan's group on creating intriguing entangled states of matter in these optical lattices. One research line I particularly like a lot is also from Adam Kaufman in Boulder, who is combining this world of optical lattices with these optical focused laser beams to move atoms around in these optical lattices, or at Stanford, Monica Schleier-Smith, working how to make these systems more programmable. Let me just at the end show you a picture, where are we going? This is a picture from one of our labs, a large-scale system with over 25,000 individual atoms. Each blue spot is an individual atom in this lattice that you can see here. So you can really also make very large systems. And we can go into these systems with these optical tweezers like Adam and move them around and place atoms at will. So what you're seeing here in this movie is atoms loaded randomly on the left-hand side. You see sometimes an atom appears. And on the right-hand side, we just create a very ordered array by moving these unordered atoms into a very ordered configuration, giving us really almost complete control, over matter atom by atom. And whenever an atom is lost on the right-hand side, for example, we can just pick up a new one on the left-hand side and bring it into space, into the right space. So this is really very exciting for quantum metrology, for quantum simulation, and I think very important for quantum computing activities in this direction. So one final application I want to mention is actually coming also from famous colleagues in the field who are using such optical lattices with atoms trapped in them to build the world's best clocks. So you might think, okay, clocks, don't we have good enough clocks already? Well, clocks are the basis for synchronization of our computing systems, computing networks, but also, most prominently, they're the basis of our navigation systems. GPS systems are connected to atomic clocks, and the better you can measure time, the more precise you can navigate. This has been the driving force of building better clocks throughout centuries of humanity. And one of the best clocks today are actually built by these atoms in optical lattices. And if you think of a clock as just as a pendulum, which you just count how many cycles you have in the pendulum, these actually work in the same way. These atoms have electron clouds, and we can start to move the electron clouds into motion. And because they're isolated from the environment, they're held in such pristine conditions, we can keep this oscillation alive basically for an indefinite amount of time, or extremely long time. And we can build clocks, or these people can build clocks, I should say, that if you would have started such a clock at the beginning of the universe, at the Big Bang, today it would only be a fraction of a second off in its time. Okay, these are extremely precise clocks, and we don't even know what the possibilities of those are going to be in the future. So I want to finish with this note that I think we really have very exciting systems in the lab, and this is pushing the research forward on all the peoples. It's basically like having, a quantum, I call it quantum universe in the lab, where we can do experiments starting from concepts connecting particle physics over material science to the physics in neutron stars to statistical physics concepts that affect our entire universe. And I also want to finish with this note. So Schrödinger was already mentioned already, and there's another famous quote from Schrödinger that I like to put in this context. So for Schrödinger in 52, this was already quite some time after quantum mechanics was invented, it was completely unimaginable to experiment with individual atoms. And now we're doing this with thousands of individual atoms that we can control basically almost perfectly. So I think this just shows how dramatically experiments can move forward and how unimaginable the experiments we're doing today were to the founders of quantum mechanics. And if you want to hear more, actually want to also advertise the next talks, Francesca and Anna are going to tell you much more about this exciting quantum world and what we can do more in these systems. And with that, I would like to leave you with this nice picture from Munich, and thank you very much for your attention.